Guys, welcome to my channel. And in today's video, I'm going to talk about introduction to VHDL. Let's begin the journey with an overview of what VHDL is, and then we'll go ahead into the depth. But before, I'm not going to explain everything in detail now, but I'm just going to give you an intro kind for this session. So, what is VHDL? VHDL is a hardware description language. That means whatever is there in the hardware that you see will be written in terms of a code, and that is how you're going to write the code. So, what is VHDL? So, V itself has got an abbreviation for itself. V means VHSIC, that is very high speed integrated circuit. So, we call it very high speed integrated circuit hardware description language. Why do we call it very high speed integrated circuits? The design that we do is in terms of transistors, and then transistors operated in nano picoseconds. So in that level we are going to program, and that's how I say that it's a high speed integrated circuit that we're going to design. There are few standards. The standards are IEEE standards. I'm not going to go in detail in it. I'm going to give you a slide later on wherein everything is there at once, so you can just have a glance. I don't think that is very much required unless you're going to do PhD or masters in it, but just for the sake of interest. So VHDL is technology vendor independent. So VHDL code can be portable as well as reusable. When I say technology and vendor dependent, I mean that VHDL is written for certain applications. It can be by developing new applications, new algorithms, or it can be used for new ICs that we get in the market. So it performs a certain task, certain function based on the vendor as well as technology. It is portable and reusable. You write the code once and that can be used for any FPGAs. Just slight here and there changes based on the synthesis tool that is being used by them, but otherwise the code doesn't change. And then VHDL allows circuit synthesis as well as simulation. What is synthesis? Synthesis is designing a circuit. What is a circuit? I have two lines here. A minute. Oops. Excuse me for this. So this is a AND gate, right? I'm going to give an input here 0 and 1, and the output is going to be a 0, right? So this is a circuit, and this circuit is a synthesis circuit. Instead of me writing and B, C is equal to A and B, and that means this is A, this is B, and this is C. You get it, right? So that is how the circuits are designed. And what is simulation? Simulation is seeing it in a time-based form, or it's like pictorial view. Give inputs and see what the output is going to be. So that is how simulation is. So let's move ahead. So these are the VHDL versions that I have spoken to you earlier. It's good that VHDL is a very old language, I must say. It's first released in 1987, and then its last release is in 2008 as per me. And there are few changes, like version change and all that, but major difference I don't think there is anything after 2008. By then everything was standardized. So VHDL is a strong language, I must say, and it's good one should know what VHDL is. Moving on, we have design flow. You can see that there is synthesis as well as simulation. These two play a major role. What is synthesis? Synthesis is the procedure that is shown in the diagram here, flowchart. So first you need to know your specifications, and after specifications you get VHDL code. Once you get the once you write the VHDL code, then you will have to analyze it and synthesize it. Here when you perform this analysis and synthesis, you will have to generate functional simulation and also generate a RTL functional netlist. When I say RTL functional netlist, that gives you the exact port mapping. It means at where your hardware should be connected. Say suppose this is your FPGA and you have written all your logic here, but externally it has to be connected somewhere. So all these are port mappings. So that has to be generated. That's what happens there in your synthesis tool. And then is your place and route. When I say place and route, if this is your FPGA, oops, excuse me. So this is your FPGA. So you write some logic here, you write some logic here, you write something here, 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 here. But exactly where it has to be placed will be decided. So that is your place and route. And it is very important. Based on place and route only, your timing analysis and all of it is done. Timing analysis is done based on the clock that you are being used. And once everything is done, you'll be generating a generate programming file. This generate programming file is the one that is used to dump into your FPGA. Based on this generate programming file, you will have all the information, all the code that you have done, including your port map, will be placed inside the FPGA. Once that is done, then you're good to go. Your algorithm is going to run into an FPGA and then you're all sorted. So first you will have to write it in write a VHDL code, and then you will have to save it with the extension of VHDL. But here one thing is your entity name and the name that you save your file with must be the same. Xilinx tool does accept it, but not all tools accept. And then you compile it using a synthesis tool. Then you do your fitting sections, then you do your timing behavior on the circuit, and then you implement your generate programming file. The programming file you can do it for FPGA, CPLD, or ASIC. So what is an FPGA, what is a CPLD, what is an ASIC is for a different video. But I think if you have come to this stage of learning VHDL, you know what these three really mean. So moving on, we have EDA tools. What is an EDA tool? An EDA tool is basically where you synthesize, simulate, and generate your file. So, for example, for Altera, which is acquired by Intel, uses Quartus tool. For Xilinx, you have ISC, you have Vivado, basically these two. For Meta Graphics, you have Model Sim, you have Precision RTL, and different companies use different kinds of simulation techniques, different kinds of synthesis techniques. You need not know them in detail, but there are few differences in terms of how the design is actually being derived. The logic remains the same. So in this diagram, I have shown you that you have a ladder, and also this is the corresponding code where you have your full adder being written. In the next slide, I'll show you how you are derived from it. So this is the basic overview. You need to have a EDA tool, and with that EDA tool, you're going to use your synthesizing as well as simulation done. So how is your code actually translated into a circuit? That is translation of VHDL code So I'm going to tell you what a full adder is going to do. So this is how the full adder looks like. It has got two inputs. It has got C in, it has got C out, it has got a sum, and this is the truth table for it. So this is the example code. Now this example code will be converted into a circuit. And how does the circuit look like? If it is an FPGA and a CPLD, this is how you're going to see the synthesis. In case if it is an ASIC model, then you're going to you see the circuit something like this. This is a CMOS logic, and FPGA and CPLD are conventional link gates. So first what you do, you have an entity. The entity name is full adder, right? So what you have to do, you have to save the file with a name called full adder. So you will save the file as fulladder.vhd, and the port you have are the inputs and the outputs. Now if you see the circuit here, you have A as input, you have B as input, but C and C out are intermittent signals. You can send them out or you can use them internally, but the end result is the sum, right? So you have A as an input, B as an input, C as an input, and you are predefining it as an input signal. And what is the vector type of it? What is it? Is it a digital? Is it, sorry, everything is digital. Is it a vector? Is it Boolean? Or is it, in Verilog we have it as reg, wires and all that. But what is it here? Is it a bit. That means it is a Boolean in your C language. As well as your sum, C out are an output, because they are the ones that are being sent out. And that also is of a bit type. So this is the entity part. What about the architecture? Architecture also has to have a name, right? So I'll tell you this architecture thing later on, but architecture has got a name. The name of it is data flow. And architecture of what? Architecture of the entity. And what is our entity? Our entity is a full adder. So we have full adder, and this is just the syntax of it. And you know that there are different types of circuit designs. One, you can define it in data flow, you can define it as structural, or you can define it as behavioral. So I'll come to that later on. But this is how the circuit is when the code is written. This is the HDL code. This will be converted into a circuit, and these circuits are these both. If it is a CPLD and an FPGA, this is the circuit. If it is an ASIC, this is the circuit. Next is a simulation. Correct. So now you see that these A and B are inputs. C is also an input. Sum and C out are outputs. The diagram here is a functional simulation, and the diagram below is a time-based simulation. Timing analysis basically. So what we have in our functional simulation, there is no delay added. So whatever is the input, that immediately you see it as an output. But whereas in your timing analysis, whatever input you give, you get a delayed output. And this delay is the clock delay, or the minimum delay that is required for the transition to happen. So now see, A is 1, B is 0, C is 0. So what is it? 1, 0, 0. 1, 0, 0. The sum of it is 1, and the C out is 0. If you add all three, just 1, so you do not have any carry bit here. So output is 1, 0. Sum is 1 and C out is 0. Similar way, you can pause it here and you can go through all the other bits that I have given here. It's a 3-bit truth table, so you can just validate through the entire design. Now let me tell you. Earlier I have told I have taken a module of a full adder, right? The entity name is full adder, and it has got one architecture. The architecture is data flow, right? Data flow is not a keyword here, but it is a structure in which we write code, right? So I can for one entity, I can have multiple architectures. So the architecture here, one is of data flow model, the architecture 2 is of behavioral, the architecture 3 is structural, and the architecture 4 can be a custom model. What is a custom model? It can be a combination of all these three, or it can be a combination of structural and behavioral. It can be a combination of data flow and structural. It can be a combination of behavioral and data flow. So it all depends on how you build the design. So at this level, I think this is good enough. Now comes the number system. You have different types of number systems. What is a number? It is a count value or a digital representation of some particular value. Integers. In VHDL, you have integers default range from 2 to the power of 31 minus 1 to 2 to the power of 31 minus 1, both positive as well as negative. I forgot to write a negative sign there, but from positive to negative, you have that integer range. What is a binary value? Your zeros and ones are a binary value. Whatever zero you write, oops. So suppose you have to write a zero. This is a zero. If you have to write one, you write one. Like that, you do not write one. So if you have to write a zero, then you will have to write something like this. You have to write something like this. If you have to write a one, then you will write something like this. This is then the first of it. In case if you have to write two digits in binary, so you write something like this. If you have to write four digits, then you just write like this. I am writing 0 here, but you can write 1 as well, or you can write up to F. These are hexadecimal values. In case if it is an octal number, you go to 0 to 7, and then you start from 1 0 7, and then 2 0 to 2 7. So likewise you keep going. So this is your binary value. Unsigned values are values where the range is from 0 to 2 power n minus 1. 2 power n minus 1, where n is the number of bits. So if you say it is 4 bit, it is to 2 power 4 minus 1. So it is something like that. You have your unsigned values, which are non-negative values. So they have to start from 0. You have no other choice. And you have your signed values. The signed values are also again negative values. So everything here is from 0 to 2 to the power of 31 minus 1 to 2 to the power of 31 minus 1. I forgot to add a negative sign there, but yes, it has got negative values to the positive range. And nevertheless, we have characters. You can ask me where characters are used, because we deal with digital values. Characters are used at the time of simulation for you to print some statements or for you to analyze something. It is not used in your synthesis statements. So here is an overview of VHDL. I hope you have understood. If you have any doubts, you can reach out to me at my email ID fpgalogic@gmail.com, or you can comment down below on what is the doubt that you have. So that is the end of my lecture for today. I'll come up with another video where I tell you what next and how to go ahead with your VHDL journey. See you for now. Thank you for watching. I hope you give you a like, share and comment, and also subscribe. Happy learning. Take care. Bye bye.